Here is our SDK Smart City scenario in Orlando, Florida. You can see we have our building shapefile data to define our cityscape. And let's zoom into our emergency response vehicle with our representative model here. On the emergency response vehicle, we have two antennas, one dipole that shows an antenna radiation pattern from red to blue being max to min antenna gain, as well as our imported antenna pattern from ANSYS HFSS. Both of these are tied to the body of our emergency vehicle, so as we animate here and watch it drive along the road, they'll always be oriented with the reference frame of our emergency vehicle. The vehicle is communicating to a network of intersection microcell base station nodes. The latitude, longitude, and altitude of these nodes are defined within SDK, and the antenna radiation pattern, again, was designed in HFSS and pulled into SDK for analysis here. The emergency response vehicle is communicating to this network of intersection nodes. You can see that they're placed at various intersections along the road. And we can look at the representative coverage of those intersections over an area of interest. So here you can see the power at the receiver, assuming that all of our intersections are transmitting signal, and we have a receiver at each of the nodes within this gridded area of interest. So you can see there are areas where the buildings are actually blocking the received power, and so that's why we have some obstruction and some of that red in those areas. But we're interested in looking at the received power along the emergency vehicle's route. So we're going to analyze the link between our dipole antenna and our intersection nodes. So here we see a link to all of the microcell nodes as our emergency vehicle drives. So this is dynamic links that are being analyzed at each time step in our simulation. We want to know the best link during our emergency vehicle route. And to define that best, in our case, we're setting the selection criteria as our maximum carrier to noise ratio. So the link is going to choose the highest carrier to noise during the dynamic movement of our emergency vehicle. And we can actually see as we animate along that that link will move and will change between intersection nodes depending on different orientations and all of the communication parameters that we've set. It'll switch its link to whichever node has the maximum carrier to noise ratio here. So we can see this visually in our 3D graphics window, but behind the scenes, SDK is always computing the corresponding analysis. So here I'm going to pull up a graph of the link between my emergency response dipole to the first 3 intersection nodes, just to keep it clear instead of looking at the full network. But you can see here the carrier to noise ratio and how it fluctuates as our emergency vehicle is moving along the road. If I pause right at the time where I have a switch from intersection nodes, you can see the reason this is happening, if I zoom into the graph, is because right at that instance, there is a jump between the maximum carrier to noise ratio from our intersection 2 to our intersection 1 node. So due to that, that's the reason that we're switching there. Next, I want to look at the comparison of our dipole antenna to our HFSS antenna. So our HFSS antenna allows us to analyze an as-installed radiation pattern, which is a much more realistic representation of our antenna. And so you can see that the blue dotted line represents our HFSS link, and it has much more fluctuation and variation as our emergency vehicle is driving along the road. So here you can see it's jumping around much more than our dipole. And this is mainly due to the differing antenna radiation pattern that we pulled from HFSS. It's much more realistic. You can see that it's much more complex. And due to that, we're going to have more fluctuations in our maximum carrier to noise ratio, and therefore more antenna switching. So just by comparing the dipole to the HFSS, you can see how adding a higher fidelity antenna from software like ANSYS HFSS is going to have a good impact on your analysis. So here we can see that our intersection nodes are then going to be communicating to a network of cell towers. So since our intersection microcell base stations and our cell towers are not moving, this is just a static link. but we do have a dynamic link from our cell towers to a network of UAV relays. So we have 3 UAVs that are moving in racetrack patterns above our area of interest. And we can see if I zoom into one of my UAVs, if I zoom into one of my cell towers, this is the antenna radiation pattern pulled from HFSS. You can see it's quite a complex pattern here. If I pull up the properties of that antenna, I'll see that it is an ANSYS FFD format. So that's pulled directly from ANSYS HFSS. Now, if I zoom into my UAV here, we'll see that as my UAV is flying along its route, it does correspond, its orientation or its attitude does correspond to the route that it's taking. So the changes in those UAVs as they're flying overhead will definitely affect the communication link that I have between my cell towers and my UAVs. So in this case, I'm interested in knowing what my best link is from my emergency response vehicle all the way through my intersection node to my cell tower node to my UAV. So this is creating a full chain link from, again, emergency vehicle to the intersection to the towers to the UAV. And so this is showing me, as I'm driving along, my best route, which was determined through Scalable Networks QualNet software.
Now we can set up our network and analyze the overall performance with scalable network technologies. We can directly set up our subsets to match our communication links and model the network performance. Now we can set up our network and analyze the overall performance with scalable network technologies. We will do this directly inside of our mission environment, as seen here. We will walk through setting up our subnets to match our communication links and model the overall performance. In this example, we'll start with our emergency response vehicle as it communicates to the nearest intersection. The intersection will let the base tower know that an EMS vehicle is responding. The nearest tower will then link overhead to the nearest UAV. We'll now play through the scenario and see how this is done. We'll start by looking at our emergency response vehicle. We'll have green lines of communication, which are being displayed from the results of scalable network technologies. This shows that a packet is being transferred. If we see a red line, this means that a packet is being dropped. Here we can get a better look as our emergency response vehicle will communicate to our intersection. The nearest intersection will then respond to the closest cell tower. Here we can see multiple intersections and multiple cell towers, which we will analyze in our network. Lastly, the ground-based tower will communicate to an overhead UAV. There are 3 UAVs for redundancy and to help our mission performance. We will now open up Scalable Network Technologies and run our first simulation to see and analyze the network performance. First, we'll start by looking at some of our general scenario configuration. Here we can see that our simulation time is 600 seconds. This is taken directly from our mission environment. Next, we'll look into our hierarchy and see how we can set up our interfaces. We'll want to recreate what we have within SCK. You can see that the interfaces are directly linked to the objects themselves and are connected through the antennas. For this simulation, we'll be using our subnets and our wireless subnet. We'll now look at the members which have been set up for us. Here we can see that we'll start at our emergency vehicle, go to our intersections, and we'll communicate to one tower transmitter. This one tower will then communicate to the overhead UAVs. We'll show how this is different as we reduced our redundancy and only communicate to one tower. We might have a worse network performance. Let's now run the simulation. Now that the simulation is complete, let's look at the results. Specifically, let's see how many packets of information were sent. Here we can see that during our 600 period of animation time, 24 packets of information were sent. We can also see the bytes and bits per second of what were sent. Let's compare this now to how many packets were received. Here we can see that only 7 packets of information were received out of the 24. Let's work on improving this by running the simulation again and now adding a collection of towers and tower transmitters that will talk to the overhead UAVs. Again, we can also compare the bytes and bits per second that were received. If we open SDK, we can also see the updated results of the green and red lines, where green is showing the packets of information that are being sent, as well as the red, which shows that our packets are being dropped. Here we can see that the emergency response vehicle is being able to send the packets, but packets are being dropped as it goes from the towers to the overhead UAV. Let's watch this closely. Let's run the simulation again. This time, we'll add a collection of transmitters on our base station towers. The intersections will now communicate to the towers. We'll now have our towers communicate to our overhead UAVs. Now that the results have been computed, we know that our communication network performance should be better, and the reason for this is because we have more ground station towers with transmitters. S&T will be able to choose the best link of communication and will be able to see the results. Let's compare the total packets that were sent and received to our previous run. Again, we can see that the same number of packets were sent. This should be comparable to our bytes and bits per second that were sent. If we look at the total packets that were received, we can see that this is increased to 14 out of 24. That's about 60% of our packets are actually received. We can also look at the bytes and bits per second. A reason that not all of our packets may be coming through is due to latency and jitter. We know that there's an average latency of 0.025 seconds of the communication links which are arriving early or late, and this may be a reason that not all of the packets made it through. Here we can now look at the simulation mission environment and again compare where the green links mean that the packets are being sent and the red links mean that the packets are being dropped. We can see that there's a different communication route which has been optimized and chosen by S&T.